Hello. In this video, we are going to be using optimization, specifically linear programming, to analyze and find the optimal decision to a marketing problem. In this situation, we are looking at two groups and trying to figure out how many offers to send to each group. And the scenario we are considering is we send an offer to each group, and then a certain percentage will take us up on the offer and request a sample. And then some percentage of those sample recipients will actually purchase the item. So this assumes that we know someone has estimated for us the percentage of each group who will request a sample after we send the invitation. And then we also know the percentage of sample recipients from each group that will make a purchase decision. And we are assuming that the cost to send an invitation to each group is known. What kind of scenario could we imagine this in? Well, back in the old days, companies used to mail out videotapes like this one. Not so much anymore, but there are lots of kinds of offers we could send out to a person. For example, like if you're trying to get people to subscribe to one of your box programs where you get something in the month, get something in the mail every month, send them out a small sample so they can get a taste of what kind of products come every month. But lots of things could fit into this sort of scenario. We are considering, like I said, two groups, and we have current customers who might be interested in this new product we're offering, and then we have new customers, people who are not currently customers of ours, but who we believe should be interested. We will let C represent the number of current customers that we will reach out to with the invitation, and N represents the number of new customers that we will be reaching out to. We assume that the current customers, 25% of them will be interested to receive a sample, and that 20% of new customers will be interested to receive a sample. Obviously, if you have different numbers, you can easily change them once we get the linear program created. Then we also assume that we know the percentage of sample recipients who will make a purchase decision. We are using 12% for current customers and 20% for new customers. Our objective is to maximize the number of new purchases that get made. We could change that to be total profits or something if we wanted to. So like I said, C represents the number of invitations we will send to current customers. N represents the number of invitations we will sell to new potential customers. It costs $4 to send an invitation to a current customer and $6 to send an invitation to a new customer. Those costs could include the cost of actually preparing the materials, the card, the package, whatever we're sending out to these people, or it could just be the cost of deciding who to send the item to. And then, like I said, the goal is to maximize the number of new purchases. We have a maximum spending budget on this of $1.2 million. This is not including the cost of the samples. This is just the cost of reaching out to the customers. And you might question that decision. We could certainly add it in and it wouldn't make it significantly more difficult. But we're trying to reach a certain number of people, and regardless of which one we're sending them to, for simplicity, we're assuming that the cost of the samples to each group is the same. Now we have a few other constraints. Number one, we want to get at least 30,000 sample requests from our current customers, and we want to get at least 10,000 sample requests from our new customers. Now we know that of the C is the number of current customers to send the invitation to, and we know that 25% of them should respond and ask for the sample. So 25% times the number of current customers we reach out to, we want that to be at least 30,000. And then 20% times the number of new customers we reach out to, we want that number to be at least 10,000. So we'll see how to write constraints about that on the next slide. And then lastly, we have a goal that the current customers should request at least twice as many samples as the new customers. So that'll be the third constraint we need to add in here. So again, our goal is to maximize sales given this budget constraint, and then these mix constraints, I'll call them. So we know that for current customers, 25% of them will request a sample and 12% of those people will actually make a purchase. So the number of sales to current customers will be 0.25 times 0.12 times the number of current customer offers we send out. And then for new customers, it's similar. It's 20% will request a sample and 20% of those will make a purchase. So the number of new customers who make a purchase will be 0.2 times 0.2 times the number of offers we send out to new customers. Now the constraints, we have $1.2 million to spend, and each current customer costs $4 to reach out to. Each new customer costs $6 to reach out to. And so you take the number of current times $4 plus the number of new times 6, that has to be less than or equal to 1.2 million. I think that's the easiest of the constraints to get your brain around. Now, like we said, we want to get at least 30,000 of our current customers to request samples. And we know that 25% of the offers we send out to current customers will result in sample requests. So we want 0.25 times the current number of customers to be greater than or equal to 30,000. Same thing with the new customers. 20% of the offers we send out will result in sample requests. So 0.2 times n should be greater than or equal to 10,000. So those three aren't too bad. It's this last one about the ratio between the current customers and the new customers that might seem the trickiest here. Now I've written it 2 times. These are 2 different ways to write them. And the bottom one is the more correct way to write it. But I think it's easier to think about it the first way to start. So the number of current customers who will respond to the offer, who will request a sample, is 0.25. And we want the number of current customers who request a sample to be at least twice the size of the number of requests we get from the new customers. So 0.25 times C should be greater than or equal to 2 times 0.2 times N. Because 0.2 times N is the number of new customers who will request the sample. And that number of requests, we want the number of current customers to be at least twice as big as the number of new customers who will request the sample. So 0.25 C is greater than or equal to 2 times 0.2 times N. So that captures the constraint that we want to ensure happens. Unfortunately, when we write it like that, we have a variable on the left side and a variable on the right side. In order to be able to solve these things, we need all the variables over on the left-hand side. So if you subtract 2 times 0.02n from both sides, we end up with the whole constraint reading as 0.25c minus 0.4n is greater than or equal to 0. And then obviously c and n both have to be non-negative. I didn't write that, but we're just going to let Excel handle that for us. So we have our linear program written out. When we go to put it into Excel, here's how I would lay it out. You can do it differently, of course. So 3% of the current customers we reach out to will make a purchase, and 4% of the new customers will make a purchase. Then you can see we have the budget constraint here. $4 times the number of current customers plus $6 times the number of new customers. With my answer here, we have a total cost of 1.2 million. We have 0.25 times the number of current, gives us 56,000, has to be greater than or equal to 30,000. And then 50,000, the number of new customers we reach out to, times 0.2 gives us 10,000, which has to be greater than or equal to 10,000. And then this ratio constraint here, we have 0.25 times the number of current, and then we have minus 0.4 times the number of new customers. That gives us 36,000, which should be greater than or equal to 0. When we solve it, we see that the final answer is the one that I was showing on the previous slide, where we are going to, let's just see here if it's going to let me draw. Hey, sometimes it doesn't. Okay, so the final answer is to reach out to 225 current customers and 50,000 new customers. And the number of new sales that we should realize as a result of this campaign is 8,750 new sales. If you look at our budget constraint here, the 1.2 million, that is binding. We are using up the full amount of the available funds. The current customer samples, we got 56,000 and that had to be greater than or equal to 30,000. So that constraint is not binding. The minimum number of new customers has to be at least 10,000 and we are going to be exactly at 10,000. So that constraint is binding. And then the constraint that says the number of new customers has to be less than or equal to 2 times the number of current customers, or number of current customers has to be 2 times or more the number of new customers that request samples. That constraint is not binding because we are sending out to 56,000, which is more than the, or 56,000 we expect is more than the 10,000 we expect from the new customers. Looking at the sensitivity report, we see here the number of new customers. Our belief based on market research is that 3% of them will purchase, and for new customers, 4% will purchase. And if this 3%, if that were to increase from 3% to 4, 5, 6%, then it could increase as much as you want. This 1e plus 30 is Excel's way of writing a gazillion, meaning some number so big it can't really tell you an exact number, just means infinity to Excel, basically. That 3% could increase as much as you want, and it wouldn't affect our answer, which makes sense. We're already doing the minimum we can outreaching to the new customers and the sending a lot more to the current customers. The current customers don't buy as higher rate, but they're cheaper to reach out to, so they're more profitable based on the numbers we've got in our particular linear program here. But the allowable decrease here is 0.003, which if you compare that to the 0.03, it's about a 10% decrease. So if that 0.03 goes down by just a little bit, the linear program will have a different answer. So that tells me that I need to make sure that I really have an accurate, that I really feel comfortable with that 3% number. If I'm not really sure, it might be worth, making sure that doing whatever I can to make sure that I really understand that number correctly. Because if that number is actually, instead of being 0.03, if it's 0.02, the linear program is not giving me the correct answer of what I should do. Similarly, with the new customers, right now it's 4%, and that could decrease by a gazillion, and still the optimal thing to do would be the decision right now, the 225,000 and the 50,000. But if that 4% were to increase by just 0.005, the optimal answer would change. So again, it's worth making sure that I really know that 4% number with a high degree of confidence. Looking at the constraints, the shadow price tells us how much the objective function would go up if we had 1 more unit of budget that we could spend. The minimum number of samples that we're trying to get from the current customers, that constraint is not binding, so it's not really affecting the quality of our answer right now. So the shadow price, if we were to change that constraint, wouldn't affect anything. The minimum number of new samples, we are expecting 10,000 and we are required to get at least 10,000. And for every unit that you would increase this, meaning requiring more samples from new customers, that would have a negative impact on our profits. And that would be true as long as the increase was less than this amount. The constraint about the number of new customers requesting samples being less than or equal to twice the number of current customers requesting samples, because that's not binding, that has a shadow price of 0 and no expected impact on our profits if we were to change that number within that range. So that was my best attempt to quickly walk you through how to formulate and solve a linear program for a customer allocation decision. I hope this has been helpful.